Hi all, hope you are safe at home and working well, following all the lectures, assessments, and things like that. Right. So today I'm going to conduct the last lecture of this series for electronic design for this semester. The last topic, our last topic is differential and multi-stage amplifiers. So out of that we will start discussing differential amplifiers. Now so far we've been discussing about amplifiers, transistor amplifiers, both BJT as well as FET. However, in those amplifiers, they were simple amplifiers like common emitter, common base, common collector, or common gate, common source, common drain. Simple small signal amplifiers. They had only one input and one output. However, now they are used for simple amplification purposes to get the voltage amplified of a signal that is having a very small voltage. Now here we will be discussing about a different concept referred to as the differential amplifier. Later on we will get to know, after doing the analysis, we will get to know that the advantages that we are having for differential amplifiers. So let's look at the basic construction of differential amplifiers. Basic construction. Now actually we have a differential pair. If you can remember, when we were talking about the op-amp construction, we talked about this differential pair, right? Excuse me. So you have actually two amplifiers in a differential manner. So we have VCC. Let's label this as RC1 and RC2, right? So two amplifier stages, so two amplifiers in fact. So you have a transistor amplifier or transistor here, two transistor stages, and another amplifier, a transistor here. So this is one side, that's one side, and here therefore this is V out 1 and this becomes V out 2. So we have two outputs in here, although in the previous cases, simple single ended amplifiers, we had only one output. Now we are taking the output across the two collectors. Earlier it was just the collector, right? Now the inputs would be the two bases. Excuse me. Now I'm drawing the simplified circuit for easy analytical purposes. So on top of this we will be having the biasing circuit, all those stuff would be there, right? As what we had in the single ended amplifiers. So this is VI1 and VI2. So these two emitters are connected to a constant current source, right? So in theoretical cases it's a constant current source, a DC constant current source, right? And then you have the ground. However, in practical scenarios, there will be a you know that the current source would have a parallel resistance connected here. So that's the practical scenario, right? You will have that resistor connected in the practical case. So this is our amplifier that we have, the basic structure, basic construction. As I earlier already said, there will be all other biasing circuits coming into play, there to bias the bases and so on and so forth. So they are not biased actually at the cutoff, they are biased at the midpoints, so that the operation is linear. Now if you derive the AC equivalent for this, right, so you have a transistor amplifier stage in here, there also you have a transistor amplifier stage. So if you try to derive the AC equivalent, you can extract actually one side in here and same would be to the other side, but don't forget that both the inputs as well as both the outputs would be there, right? So if you draw the AC equivalent, right, if you try to draw the AC equivalent for this, it will look like you have the two resistors. You can, I think you can remember the construction that you had. You have the two collector resistors, right? I'll first draw one side. It's easier for us to use the common base model in here, right? So that will be with RE, right? This is your input, this is your RC1, right? And the other side also you will this is your input, right? This is your output, V out 1, right? And the other side also you will have let's not label this one for the moment, RC2, and because this is the DC supply, this is a virtual ground for the AC equivalent, and now the same construction would come. You can also draw the equivalent circuit with me, right? So you will also learn, right? Yeah. Now here what we have is RE, right? And RE, identical transistors and identical resistors as well in here. So RC. However, the input would be across these two. So this is your V out, right? V out is V out 1 minus V out 2, and this is your input, right? The input actually will be between these two. We'll first draw the rest of the circuit. So you had that resistor there, right? That will not go off in the case of AC, right? So resistors would be there. So I replace the transistor of this circuit, right, with the this transistor with the common base model, right? So we'll label that as using CB model, right? Common base model for the transistor. We get this equivalent circuit, right? So AC equivalent circuit, and our input would be this, right? So this is my input, which is V differential, the differential input, and this is V out differential, the differential output, right? Now by considering the symmetry, because you can see, you know that this is a symmetrical circuit and this side is identical to this side, so the voltage input is between these two resistors, so we can divide that into two halves on either side, right? So that is this side would be VDD by or rather VD by 2 positive and this is actually in this direction, it will be minus Vd by 2. So that is considering symmetry. You get double M, right? Symmetry. You can actually divide that, Vd into Vd by 2 and minus Vd by 2 across the two emitter resistors. Now we have a circuit that actually can be converted into two equivalent circuits, right? So in the case of equivalent circuits, we can take one side at a time. Now in that case, when it comes to the transistor, that the differential input is given between these two, so therefore in the AC equivalent there won't be any current going in this resistor, so therefore that resistor will also become not actually meaningful, right? So no current in AC, right? So therefore this point becomes a virtual ground, right? Virtual ground. So considering all these matters, if you draw the two side amplifiers or two amplifier stages, you will get, for this one you get so you have the base, right? Now what we do is actually from this we can if you take this circuit again, let's take this circuit again, we will be going around with a different equivalent now, right? So it's, if you take this circuit again, by considering all these symmetries, after considering all these symmetries, if you take this circuit again, let's go to a new page, that would be easier for us. So this is our circuit. So if you delete this, and you don't need this as well, right? So let's draw it in black. So this is our R, right? R is there, there will be I. Did I mark the I there? I don't think so. So this is our I, right? I is there, R is there, okay. Right, so with that we can actually take this input as Vi1 as Vd by 2, and this as minus Vd by 2. Now for these two circuits we can draw the AC equivalent again using the common emitter mode, common emitter configuration, or common emitter equivalent, or hybrid pi equivalent. That will be for one input. I mean, it will be actually the equivalent circuit would look the same, right? However, the input values, output values will be little different. So if you use that, right, so you have R out, that's inside the transistor, right? And then we have RC here. So I'm using the knowledge that you gathered in the second year, as well as we've been using that in the third year, right? And this is my V out one, right? And this is my Vi1, right? Okay, so actually the V out 1 is this, right? So this is V out 1, we can say, and this is my Vi1, which is Vd by 2, right? So same construction is there. So for the other one, I mean the other side, it's actually exactly the same, right? Exactly same diagram would be there, but for the voltage values would be different. Now the other input, as you can see here in this diagram, that is in this diagram, it will be minus Vd by 2 the input, and this is Vd Vi, oops, we have to use black, Vi2, and this is also V out 2, right? But the values are the same. This is R pi, right? R pi, this is R pi, this is minus, or rather Gm V pi, and this is also Gm V pi, right? That's from the knowledge that you gathered from last year, as well as we've been talking about effect amplifiers this year, right? So now from this is the simple most circuit that we had last year using BJT amplifiers. So for Q1 we can write V out 1 is equal to minus Gm Vd by 2, right? Gm Vd by 2 into Rc dash. Rc dash here is Rc parallel R out, right? So Rc dash is R out, Rc parallel R out. So for Q2, can you write that equation? Is it much different from the previous one, or it's just a matter of put in this Vd Vd minus Vd by 2 in the place? So in that case it will be V out 2 equal to Gm Vd by 2 into Rc dash, right? Or if you write it properly, this will be minus, right? So if you combine these two together to get that is get V out differential, V out differential is from this circuit, you know. Okay, here V out differential is this, right? So V out differential is V out 1 minus V out 2. So from that, V out 1 minus V out 2, which is equal to minus the value here is the same, but this 12 will be negative, this is negative and this is positive. So if you take V out 1 minus V out 2, you get twice of this. So minus Gm Vd Rc dash, right? So Rc dash is equal to Rc parallel R out, right? So that's the case. Now the differential gain, right? Now the differential gain, A differential is equal to V out differential divided by Vi differential, right? Or V differential, Vi differential is V differential. So V out differential is, we have got that value, minus Gm Vd Rc dash divided by Vi differential is Vd, which is now equal to Gm Rc dash, right? Again, Rc dash is equal to Rc parallel RL, R out, Rc parallel R out. So now that's for the differential input, differential mode signal or differential input, right? So this is for differential input. Now what about for a common mode input? So we will take it right, differential input. We will see what about for common mode signal now, right? Let's use a new page. Common mode signal. Now what is known as a common mode signal? As any signal that is common to both the inputs, right? So I'm using some trick here. Okay, so I'm going to copy this circuit for my simplicity or for my benefit, right? This is my circuit, so I'm going to copy it and paste it in here, right? So we can delete the unnecessary stuff. Yeah, right. So this is not the case now, right? Oops. Now we apply a common mode signal, right? Common mode signal means we apply the same signal to both the inputs. Now what is the purpose of doing that? This is V common. Now in both the cases it's V common. What is the purpose of doing this? You know, the noise, right? So the noise is available in both the inputs, right? So let's say you are giving a differential input, so that is an input between these two, right? So V1 and Vi1 and Vi2. There can be noise which is common mode signal, which is a common mode signal. The two terminals would have the same noise. So what we do now is see if what would happen to that common mode noise, right? So common mode signal. So that is why we look into this this common mode. If you apply common mode signal, what would happen? Now we know that this is symmetrical, right? And a same input is given. Now earlier it was a differential input, and that input was dropped across this line, so we got rid of this resistor. But now it is not the case. Both signals are common and those are connected with respect to the ground, right? So therefore what would happen now is we can actually think by considering the symmetry, right? Considering the symmetry again, right? We can split this single resistor into two equivalent resistors or two weighted resistors on either side. So what would be that weighted resistor now? 2R. Why 2R? When you put these two R's together or in parallel, it will give us this resistance. So these two in parallel will give us this resistor, right? So now let's redraw this circuit. I'm again going to use the same copy, right? That is for my easy work, right? VCC, but now this part would change, right? So this is V common, right? Oops, we use V there. V common, and this is also V common. This is not there. Right, but this part now we are going to change, right? This is what actually we divided into two. So the current source will also be split into two now, right? So that is only for common mode case, right? But it is not the general case, it is only for common mode case. So what we can do is we can have a 2R resistor here, a 2R resistor here, and a current source. How much would be the current source? Now the addition of these two currents should be the total current that we had earlier. So in that case, this has to be I by 2. This has to be I by 2. This is 2R and this is 2R. Now if you think of this case, right, so I by 2 going across 2R will generate the same voltage as what we had earlier, right? We had I going through R, which is IR, and here we have I by 2 going across, going through 2R, so it is again IR, right? So same voltage. So that is why I said it is we can split it into equivalent parts, and they will give you the right effect, right? So I is like that. Okay, I by 2. Now we will derive the AC equivalent for this, right? So AC equivalent, if you draw the AC equivalent, we have RC, right? And we have V out 1. The transistor is modeled as common base model, right? We use common base model here, RE. Then you have 2R here and the ground, right? And this is my V common, right? V common is, I'll use a different color for that, or maybe it's okay. And this is my RC, and that's my ground, right? Again, it is the ground, and this is IC, and this is IE, right? IE goes across that, and it is the same case for the other transistor as well. We will draw that. We will have RC, right? The transistor, RE, 2R, and the ground, right? So this is 2R, this is RE, this is my again V common, and V out 2, RC, and this is the ground for AC. So you just go back, if you can't remember how to derive the AC circuit, you will have to go back and get that revised, right? IC, we've been doing that in the first topic as well. So this is IE. So two identical sides, but the difference is that this is V out 1 and this is V out 2. So we are going to measure the voltage error between these two, because that is our output, right? Now what is IE? IE in this case, using Ohm's law, is equal to V common divided by RE plus 2 R, right? Also we know from the relationships IC is equal to alpha IE, which is alpha V common divided by RE plus 2R. Now what is V out? V out 1 from this circuit, right? V out 1 is the output voltage with respect to the ground, which is minus ICRC, right? Minus ICRC, which is minus alpha V common RC divided by RE plus 2R, right? RE plus 2R. So it's the same case for V out 2 as well. V out 2, if you use the right hand side circuit, it will give us the same value, which is minus IC, I'll draw the minus little larger, ICRC equal to minus alpha V common, because now it is the same voltage given. This is not RC, right? It is, yeah, RC divided by RE plus 2R, right? So now what happened? Now V out is equal to V out 1 minus V out 2, which is 0, right? So common mode signal will not be amplified, right? Common mode signal will not be amplified. If it is a perfect perfect differential amplifier. Now you see the main benefit of the differential amplifier, right? The differential amplifier does not amplify the common mode signal, meaning that noise will not be amplified. So which is very good for filtering purposes, so filtering out the noise, right? Any additional noise that is imposed in the signal, common mode signal or common mode noise, will be actually not amplified, meaning that it will be suppressed by this amplifier. Now this is if it is ideal case, which is perfectly matched transistors, same gain, same beta, same alpha, and so on and so forth. However, in practical scenarios, there will be a little difference between the beta values of the two transistors, even if they are from the same batch. So in that case, there will be a very little output voltage because of the common mode signal in practical scenarios. But the common mode signal will definitely be suppressed to a great extent, which is very, very useful when it comes to noisy signals, right? When there is common mode noise. Now if the signal actually contaminates noise, then we can't help with this one. But if the noise is added during the transmission, traveling from the signal source to the amplifier, that is as common mode, because two wires, now let's say, so two wires going in close proximity, any noise, additional noise will be induced on both these, right? So therefore it will become a common mode noise, and that can be actually completely leaves aside from the ideal differential amplifier. With a practical differential amplifier, even it is suppressed to a great extent. Now as a summary, we can write, we know we had the differential gain AD was equal to minus GM RC dash, right? And A common common mode gain was 0, right? So that's for differential output, right? If you take the output as differential. Now the next case, so here again the inputs are, right, VI1 and VI2, and VD is VI1 minus VI2, and V common is VI1 plus VI2 over, right, the common mode gain. So that is why it was divided by 2, right? So right now the general case, now we got actually the differential mode separately and common mode signal separately, but in general case V out will be A differential VI, V differential plus A common V common, right? So that is how it is in the generic case. So as you can see here, because the common mode amplification is 0 for the differential output, you get the common mode signal suppressed fully, right? So if you have a very tiny common mode gain, then that part will be there in the output, right? That's for a common mode input signal. Now for a single ended input, this is for a for common mode input, for common mode input, right? What about for different single ended input? The single ended output, that was what we derived earlier, that is what you have in here, right? So okay, not here, but I think this one, right? This one, right? So in that case the gain actually is where is it? Alpha. Where do you have that? There you go, right? So this is for single ended output. So single ended output is alpha RC over RE plus 2R, right? Because this is your input, so the gain would be minus alpha RC over this. So let's write that in here. So the differential or single ended output is minus alpha. This is not actually single ended output, this is single ended gain, right? So single ended gain. So for single ended output, single ended gain is minus alpha RC over RE plus 2R, that is if you apply a single ended case. So that is deducing from the common mode gain calculations. Now we define something named as common mode rejection ratio. Common mode rejection right? Common mode rejection ratio, or abbreviated as CMRR. That is CMRR. CMRR. Oops, sorry. Okay, so CMRR is defined as the differential mode gain, A differential divided by A common, that's for a single ended output, right? Single ended output. So in that case, for a single ended output, for single ended output, A differential is equal to minus GM RC dash over 2. We got that earlier. And A common mode gain is minus alpha RC divided by RE plus 2R. Can be approximated by neglecting the RE. We can approximate that into minus alpha RC over 2R, because 2R is much larger. This is a resistance of a current source than even twice that, so it is much larger compared to RE. So taking that into consideration, we can approximate this factor into minus alpha RC over 2R. So in that case, what is CMRR? CMRR is equal to mod of, what you have here is minus GM RC dash over 2 divided by minus alpha RC over 2R. So we get the equation mod of GM RC dash, 2 cancels out, over alpha, I think R was there, R over alpha RC. Now RC and RC dash is the parallel combination of R out and RC. R out is very large, so we can approximate these two together, which will cancel out this as well. So approximates to GM R over alpha, right? That is because RC dash is approximately equal to RC, right? RC dash is equal to RC dash parallel R out, right? So RC dash is approximately equal to RC dash is approximately equal to RC, right? So usually common mode rejection ratio is usually given in dB, right? Usually CMRR is given in decibels. You can see this figure in op amps, right? CMRR, because op amp, when we look at the construction of op amp, we saw that it is actually the combination of differential stage. What you have at the very beginning is differential stage, and then you have a stage to combine the differential output into a single ended output, and then another gain stage. So therefore again the second stage and the third stage, there is no differential case, so it is actually usual, more or less like a normal amplifier. So rejection ratio is mainly because of this differential amplifier stage, right? Okay, so that is that for the differential amplifiers. Now we look at multi-stage amplifiers. Now, can you remember we were talking about multi-stage amplifiers. So we actually had so far in last year as well as this year, and the beginning, the first topic with FETs, we had single stage amplifiers, right? Only one transistor was there. Now what if we have more than one transistors in our amplifier? Multi-stage amplifiers, or we call it as one thing that I forgot to mention, that is when we were talking about differential amplifier, there is a symbol for differential amplifier. So the differential amplifier is symbolized. Oops, I have not enabled this feature. Okay, let's do that. Right. Oops, it has to be a straight line, right? Okay, that's your differential input, and that's your differential output, right? So VI1, VI2, Vout1, and Vout2. So that's the symbol for the differential amplifier, right? Okay. Now let's look at multistage amplifiers, or cascaded amplifiers, right? Cascaded means the output of one stage is given to the input of the other stage. So let me draw biasing circuit first, right? So let me draw an amplifier circuit. We have the collector resistor here, emitter resistor here, then you have okay, that's the circuit that you have, right? So, and if I duplicate this, right, I'm going to have two of those, and now let's start labeling them, right? So Q1 is there, Q2 is there, right? Q1, Q2, right? Two amplifier stages. Let's connect them in the supply and the ground. So that's ground, that's VCC, right? So RC1, RC2, RE1, RE2, and we will construct two common emitter stages in here. So you have a capacitor here, CE1, and another capacitor here, CE2, oops, CE2, and R1, R2, R3, R4, right? Okay, so let's give the input to the base of the first amplifier, right? So we will be having RS and VS as usual. VS is there, RS is there. Then we will take the output from the collector of the second transistor, RL. Now we will connect the output of the first transistor, which is the collector, which we get from the collector, to the input of that is the base of the second transistor, which we will label as C1. Now this is a cascaded amplifier stage, or multi-stage amplifiers, two amplifiers connected together or cascaded together. So let's start drawing the AC equivalent. This is actually very it is the same amplifier duplicated or doubled. These stages may be configured to different gains, different transistors may be there, so that is not a problem here, right? So AC equivalent, if we draw the AC equivalent for this, let's start with the using hybrid pi model or common emitter model, right? So you have this out, and for that transistor, so this is that, I'm going to label that like that, right? So that's our transistor. Beyond the transistor, you have on the left hand side you have these two transistors. Let's label this that as RB1. So okay, RB1, where RB1 is R1 parallel R2, right? So then we have the RS, right, and VS. Okay, now what next? We have this R pi, right? Let's assume that it is the same transistor, or R pi 1 actually, different transistor R pi 1, and you have GM1 V pi 1, right? Usual parameters or representations. And on the output side you have this is bypass, so this becomes the ground. RC1 is there, right? RC1 is there. Now let's leave this part little like that, and we will draw the other side. So the other transistor will also have the same construction, right? All these components are there, so I'm going to copy this and paste it, but we'll label them separately, right? So that's my second transistor. So in the second transistor we have this is pi 2, right? This is pi 2 and RB2. So RB2 is equal to, according to this transistor, this circuit, R3 parallel R4, right? What is RB2? R3 parallel R4. Now this has to be GM2, GM2 V pi 2, R pi 2, RB2, RC also 2, RC2, right? Is that RC2? Yeah, yes, right, RC2. RE2 is bypassed. Now as you can see here, this C1, what is the replacement for that C1? You can remember, right? We did it in the second year electronic fundamentals module, which is a short circuit, right? Yeah, a short circuit. So that does mean that, okay, this is fully connected, meaning that this is connected. Now collector of this, that is this point, is connected with the base of this, so that is this, right? What else do we have? Tell me. There is something more, right? Oh, I have forgotten to label this, right? This is our V out. Okay, that indicates that this R out, RL has to be here, right? So that is RL is here, and we get the output across this V out, right? I think the entire circuit is now completed. Okay, so let's label this stuff. This is V pi 2, intermediate voltages V pi 2, this is V pi 1, right? So V pi 1 and V pi 2 we have labeled. Now let's label this, or let's go ahead with the calculation, right? So AV for the whole amplifier is V out, is equal to V out over Vs. Now V out over Vs is V out over V pi, or let's label it in a different way as well, as this intermediate voltage as V1, right? So we can label this as V out over V1, that is for the first stage, and V1 over Vs, V1 over Vs for the first the other stage, so second stage and the first stage, so which is actually A1 into A2 cascaded, right? But there is little difference in here, of course, because these are loaded into this. Let's look at what actually we will be getting, right? So V out can be written as, or alternatively AV can be written as V out over Vs, which is equal to V out over V pi 1, V pi 2, then V pi 2 over V pi 1, and V pi 1 over V S, right? So let's go ahead and do that. What is V out? V out is equal to minus GM 2, right? That is GM2 minus GM2 V pi 2 RC or RL parallel RC 2 parallel R out 2. So this is R out 2, right? This is R out 1. So that's GM V pi 2 RL parallel RC 2 parallel R out 2, right? Into V pi 2. Then V pi 2 from this, right, is equal to what? Minus GM1 V pi 1 minus GM1 V pi 1 into what? RC1 parallel RB R out 1 parallel RB2 parallel R by 2. So that is RC2 parallel R out 2 parallel RB2 parallel R by 2, right? Then we have V pi 1 from this circuit is the voltage divider, that is RB1 parallel R pi 1, right? RB1 parallel R pi 1 divided by RB1 parallel R pi 1 plus R pi 1 into Vs. This can be approximated actually to Vs, because the reason is R pi 1 is much smaller than RB1, right? Now from these three we can derive the overall gain. Therefore AV is equal to, we will have this minus GM2 minus minus will become plus, right? So plus GM1, so GM1 GM2 GM1, oops, GM1, GM2, right? RL parallel RC2 parallel R out 2, then RC2 parallel R out 2 parallel RB2 parallel R by 2. If I take this as well, right, RB1 parallel R by 1 divided by RB1 parallel R by, oops, parallel R by 1 plus R by RS. So here I did a mistake here, this is RS. So RS is much smaller here, right? RS is much smaller compared with that RB1 parallel R by 1. You have it, but if you want to keep it, you can keep it, right? So here though we have a little problem to be discussed. So this is actually our gain, right? But we can use the maximum power transfer theorem in here, right? You know that there are two stages. This is an output stage and this is an input stage, so which is actually separated at this point, right? It is separated at this point, right? So the output impedance, if you look at this, is as R out, this as Ri, right? As so R out 1 and Ri 2, output impedance, output resistance of the first stage and the input resistance of the second stage, they have to be matched, right, according to the maximum power transfer theorem, right? To maximum power transfer theorem, right? R out 1 has to be equal to R in 2, or in general R out of the end stage should be equal to Ri of n plus 1 stage, right? So that's the criteria that has to be satisfied in order for the maximum power to be transferred from one stage to the other stage. So impedance matching is required to get the maximum benefit or maximum out of this transistor, or rather the cascaded pair, right? If you have cascaded amplifiers or multi-stage amplifiers, you need to satisfy this criteria. We know that according to the maximum power transfer theorem, whatever the load that you feel has to be equal to the Norton's resistance or Thevenin's resistance. So in that case, in this case, RB2 parallel R by 2 should be equal to RC1 parallel R out 1, right? So this will give us actually RB2 parallel R by 2 should be equal to RC1 parallel R out 1, right? So that is how it is by looking at the circuit. So if you have that, then you will get the maximum power transferred from one stage to the other stage, right? So I think that's all for the semester for the electronic design, and you can we will have some discussions in future. In addition, you can always communicate to us via WhatsApp if you have any doubts in the sections, So stay home, stay safe, work well. So catch you in a discussion session later on. See you all.